One of the periodic trends that really relies on a knowledge of bonding is the melting point trend for the periodic table. Now, this is one that you need to be familiar with for multiple choice questions on paper 1. On paper 2, it's a bit easier in that you have section 7 of the data booklet, which has all the melting point data for you, but then you need to be able to explain why the trends are what they are based on the particular types of bonding involved. So the melting point trends you need to be able to explain are melting points down or up or down group 1 of the periodic table, the group 1 metals. You don't need to worry about hydrogen since it's a bit of an outlier in that group. You have to be able to explain the group 17 melting point trend, up or down, and you need to be able to explain the period 3 elements, their melting point trend. Here and here. Now the period 3 one I have sort of separated here into the metals, since we're focusing on metallic bonding right now, but also across period 3 as a whole. So let's start with the metals metallic bonding. So to think about metal melting points, you have to think about the strength of the metallic bonds. A metallic bond is the attraction between positive ions and delocalized electrons. So if you can increase the charge on that positive ion, then you will increase the attraction between the ions and the delocalized electrons. And as we go across period 3 for metals, you go from sodium to magnesium to aluminum. Now, as we increase the charge on the ion, we're going to increase the electrostatic attraction for the delocalized electrons. That means we've increased the metallic bond strength. In addition, as metal ions become more positive, they get smaller. So this one is sort of a double whammy, if you will, of factors that are changing here. We're not only increasing the charge on the ion, we're actually also decreasing the ionic radii of the ions. So we have two different factors, both of which are increasing the charge density on the metal cations, and that's going to increase the electrostatic attraction for delocalized electrons, which is what the metallic bond is. So the strength of the metallic bond is going up, the melting point of the metal will go up. So it's very similar to a concept of like lattice enthalpy, where the attraction between ions is increased as we get more charge density, so higher charge or smaller ions, or a combination of both. Same idea here for metallic bond strength. As we go down the group for the metals, we're still in a frame of mind of thinking about metallic bonding. Again, the attraction between positive ions and delocalized electrons. But all the group 1 metals have the same 1+ charge, so we can't focus on the charge, and instead we have to focus on the size of the atoms or the ions. So as we're going down the group, we have increasing ionic radii. We know that's going to decrease the charge density on those metal ions, and therefore we're going to decrease the electrostatic attraction for the delocalized electrons. So we're decreasing the metallic bond strength, and we're decreasing the melting point. So trends that involve metal elements have to be focused on their metallic bonding, which means they really have to be focused on the metal cations and what's happening to their charge, their size, their charge density, because that has a direct impact on how strong the metallic bonds are. Now, when you get to group 17, though, now we're dealing with the halogens. So we're not in the covalent bonding unit, but you're expected to remember that the halogens are diatomic molecules. They're part of our Brinkelhoff series of elements, so they all exist as diatomic molecules, which means that their melting points don't depend on metallic bonding. They also don't even depend on covalent bonding. They depend on IMFs. And the IMF that these will have between their molecules, because they are all simple diatomic nonpolar molecules, is London forces. And the main factor for London forces is surface area, or number of electrons. So as we go down this group, we are increasing atomic radii. The atoms involved in the molecules are getting bigger. We're increasing the number of electrons, and we're increasing the surface area. And all of those things lead to an increase in the strength of the London forces. And if London forces go up, we're going to have an increase in melting point. So it's the opposite trend of group 1, because group 1 is metals and group 17 is nonmetals. They have different kinds of attractions between the particles, so they follow different rules, and so we end up seeing different trends. Iodine is a solid at room temperature, bromine is a liquid at room temperature, and fluorine and chlorine are both gases at room temperature. So that follows the melting point trend that we've described here. Finally, the last melting point trend that you could be asked is across all of period 3. Now this is kind of this overall bonding question. You start off with Na, Mg, and Al, which are metals. And we already described that trend at the top, that as we go to the right, we increase the charge on the metal ion, positive ion, and that increases the metallic bonding strength. So across these first 3, we would expect the melting point to go up. If you look at the values, the next value is silicon, which is even higher than aluminum, significantly higher, like 700 degrees higher. And that's because silicon is a giant covalent structure. And giant covalent, having covalent bonds to all your neighboring atoms in a giant crystal, is usually thought of as being sort of the strongest net bonding that you can have between your atoms. So you've got metallic bonding increasing as you go across and getting higher charges on the metal ions. Then you have this big jump up to the silicon with a giant network covalent. And then you go to nonmetals. You go to phosphorus, sulfur, chlorine, and argon. All of those are nonmetals. So phosphorus, sulfur, and chlorine are all molecules. So they're going to have weak IMFs. And then argon is just a single atom. And so it also can have very weak London forces since it's very small. Now, they're all going to be, relatively speaking, way down here. If this were melting point on a y-axis. Technically, there's like this is the formula of phosphorus. Sulfur is a little higher because it's a slightly larger molecule. Chlorine's a little lower because it's a smaller molecule, and argon would be the lowest because it's the smallest. It's only one atom. But the key idea would be these ones, their melting point is based off of very, relatively speaking, weak IMFs based off London forces. The ones on the left are metals based on metallic bonding, which is pretty strong and increases as we go from left to right. And then at the top is giant covalent structures and covalent bonding, giving the highest melting point.